In this video, we're going to look at the calculus of the hyperbolic functions and how it can be used to widen the range of functions that we can integrate confidently. So, the following results are almost immediate from the definitions of the hyperbolic functions. If we've got y equals sin x, which we know is e to the x minus e to the minus x divided by 2, then dy by dx is just going to be a half of e to the x plus e to the minus x. In other words, the derivative of sin x is cos x. And if we've got y equals sin kx, then simple use of the chain rule will give us dy by dx equals k times cos kx. On the other hand, if we have y equals cos x, which is e to the x plus e to the minus x divided by 2, then differentiating it, we get dy by dx is going to be a half of e to the x minus e to the minus x, which is of course sin x. So the derivative of cos x is sin x. And if we have y equals cos kx, then again the chain rule is going to give us dy by dx is k sin kx. If we have y equals tan x, which we know is sin x divided by cos x, then we can use the quotient rule to find the derivative of tan x. So differentiating the sin x, we get cos x times by the denominator, which is cos x. Then we've got to take away the sin x left alone, times by the derivative of the denominator, and the derivative of cos x is itself sin x. So we get dy by dx equals cos x minus sin x over cos squared x, which is cos squared x minus sin squared x over cos squared x. But we know that cos squared x minus sin squared x is always equal to 1. So we've got dy by dx is 1 over cos squared x. In other words, dy by dx is sec squared x. And if we have y equals tan kx, then we have dy by dx is k sec squared kx, using the chain rule again. So for our first example, we're going to try and prove that the curve y equals cos squared x minus 6 sin x has just one stationary point, and we're going to determine the exact coordinates and the nature of that stationary point. So with y equals cos squared x minus 6 sin x, to find the stationary point we must do some differentiation. So we've got dy by dx is first of all the derivative of cos squared x, and using the chain rule, the derivative of cos squared x is 2 cos x sin x. And then we need to subtract the derivative of 6 sin x, which is simply 6 cos x. So the derivative of our function is 2 cos x sin x minus 6 cos x. For a stationary point, we need dy by dx equals 0. So that gives me 2 cos x times by sin x minus 3 must equal 0. So I've done a simple factorisation on dy by dx expression. So that means that either cos x equals 0 or sin x equals 3. We know that cos x cannot equals 0, has no solutions, because we know that cos x is greater than or equal to 1 for all values of x. So that simply leaves us with one stationary point, which satisfies sin x equals 3. And we know we've only got one value there because sin x is a one-to-one function. So each value of sin x comes from a unique value of x. So we've got only one stationary point. The stationary point satisfies sin x equals 3. So x must be sin to the minus 1 of 3. And that, in its exact form, expressed as a logarithm, is the logarithm of 3 plus root 10. Remember that sin to the minus 1 of a value is the natural logarithm of the value plus the square root of the value squared, add 1. So we've got the x value there is the logarithm of 3 plus root 10. Now, if sin x is equal to 3, then we know that cos squared x minus sin squared x is always equal to 1. So cos squared x is definitely equal to 1 plus sin squared x, which in this case is 10. So the value of y that we've got is y is equal to cos squared x minus 6 sin x. So that is 10 take away 18, which is minus 8. So we now know that the coordinates of the stationary point are, the x-coordinate is ln of 3 plus root 10, and the y-coordinate is minus 8. We haven't yet classified the stationary point. Well, we know that dy by dx is 2 cos x sin x minus 6 cos x. So we can find d2y dx squared reasonably easily. To differentiate the 2 cos x sin x, we can use the product rule. So that's going to give me 2 sin x plus 2 cos x. And then the derivative of 6 cos x is simply 6 sin x. So we've got d2y dx squared is equal to 2 sin squared x plus 2 cos squared x minus 6 sin x. Now at the stationary point, we know that sin x is 3 and cos squared x is 10. So we've got 2 times 3 squared, which is 18, plus 2 times 10, so that's plus 20, take away 6 times 3, which is take away 18, which actually gives me 20. So d2y dx squared is definitely positive, which means that the stationary point is a minimum. The differentiation results that we had immediately give us some integration results. We know that cos x is the derivative of sin x, so therefore the integral of cos x is sin x plus the constant of integration. The integral of cos kx, well, we know that k cos kx is the derivative of sin kx. So cos kx is the derivative of 1 over k sin kx. So the integral of cos kx must be 1 over k sin kx plus c. Similarly, we know that the integral of sin x is going to be cos x plus c, and the integral of sin kx will be 1 over k cos kx plus c. We know that the integral of sec squared x will be tan x plus c, and the integral of sec squared kx will be 1 over k tanh kx plus c. So, as a second example, let's have the function f of x is x sine 2x, and let's evaluate first of all the derivative of f when x equals ln 2, and then secondly the integral between 0 and ln 2 of f of x dx. So using the product rule, we've got f dash x is going to be 1 times by sine 2x plus x times by the derivative of sine 2x, which is 2 cos 2x. If x is equal to ln 2, then 2x is 2 ln 2, which is the same thing as ln 4, which means that e to the 2x is 4, and therefore sine 2x, which is going to be a half of e to the 2x minus e to the minus 2x, is going to be a half of 4 take away a quarter, which is 15 over 8, and cos 2x is going to be a half of e to the 2x plus e to the minus 2x, so that's going to be a half of 4 plus 1 over 4, so that gives me 17 over 8. So we're going to get that the value of the derivative of f when x equals ln 2 is going to be 15 over 8 plus 2 times ln 2 times by 17 over 8, which we tidy up a little bit as 15 over 8 plus 17 over 4 times ln 2. For the integral of f of x, we're going to need to use integration by parts. And using integration by parts, we're able to say that x sine 2x is first of all going to be the integral x times by the integral of sine 2x, which gives me x times a half cos 2x. But then I must subtract the integral of the first bit differentiated times by the answer to the second bit integrated. So in this case, the first bit differentiated is 1. The integral of sine 2x is a half cos 2x. So I've got to work out the integral of a half cos 2x, and the integral of a half cos 2x is a quarter sine 2x. So I'm ending up with my final integral being a half x cos 2x minus a quarter sine 2x. I'm not going to put the plus c in this case because I'm going to be doing a definite integral anyway. I want the value of the definite integral. Okay, so the integral between 0 and the logarithm of 2 of f of x dx is going to be the value of a half x cos 2x minus a quarter sine 2x when x equals ln 2. Take away the value of that expression when x is 0. Now, we on the previous page worked out that when x is ln 2, cos 2x was 17 over 8 and sine 2x was 15 over 8. So when I substitute ln 2 in, the value of my expression is a half ln 2 times 17 over 8 minus a quarter times 15 over 8. When I substitute x equals 0 in, I simply get 0 take away 0. So my final answer for the integral is going to be 1/32 of 34 ln 2 take away 15. For example 3, we've got to find the integral of cos squared 5x. Now, we know that cos squared a minus sin squared a is also always equal to 1, and that cos squared a plus sin squared a gives me cos 2a. So if I add those two expressions, I'm going to get 2 cos squared a equals 1 plus cos 2a. In other words, cos squared a must be a half of 1 plus cos 2a. So that means that I can rewrite the integral of cos squared 5x as being the integral of a half plus a half cos 10x, which I can write down straight away as being a half x plus 1/20 of sin 10x plus the constant of integration. Alternatively, what we could do is we could say that we know that cos 5x is a half of e to the 5x plus e to the minus 5x. So cos squared 5x is going to be a half of e to the 5x plus e to the minus 5x all squared, which gives me a quarter of e to the 10x plus 2 plus e to the minus 10x. So we can say that that is 1/2 plus a quarter e to the 10x plus a quarter e to the minus 10x. So the integral of cos squared 5x dx is going to be the integral of a half plus a quarter e to the 10x plus a quarter e to the minus 10x, which gives me, when I integrate it, 1/2 x plus 1/40 e to the 10x minus 1/40 e to the minus 10x plus c. And it's fairly easy to show that that's exactly the same as 1/2 x plus 1/20 sin 10x plus c. Okay, either of those two answers would be acceptable for the integral of cos squared 5x. Now we've looked so far at the calculus of the hyperbolic functions. We're now going to look at the calculus of the inverse hyperbolic functions. And the results here are most easily established if we use a little bit of implicit differentiation. So if I've got y equals sin to the minus 1 of x, then that tells me that sin y must be equal to x. If we now differentiate each side with respect to x, then we get cos y dy by dx is equal to 1, which gives me dy by dx equals 1 over cos y. However, we really want dy by dx to be given as a function of x. Now, we know that cos squared a minus sin squared a is always equal to 1. So we can say, certainly, that cos squared y minus sin squared y is definitely equal to 1. In other words, cos squared y must equal 1 plus sin squared y. But sin y is x, so we've got cos squared y is definitely equal to 1 plus x squared. So that tells me that cos y must be equal to the square root of 1 plus x squared. Now in this case that is definite because cos y is definitely a positive number. So we don't need to consider the possibility of cosh y being the negative root of 1 plus x squared. So we now know that dy by dx is 1 over the root of 1 plus x squared. So if we've got y equals sine to the minus 1 of x, then dy by dx is 1 over root of 1 plus x squared. So that's our first differentiation result for an inverse hyperbolic function. Now let's have a think about cosh to the minus 1 of x. If y equals cosh to the minus 1 of x, then by the definition, y is the positive value that satisfies cosh y equals x. So now if we differentiate each side with respect to x, that gives me sine y dy by dx equals 1. So dy by dx is 1 over sine y. We've now got the fact that sine squared y equals cosh squared y minus 1. But cosh y is x, so we've got cosh squared y minus 1 is just x squared minus 1. And we have got, therefore, that sine y is plus or minus the square root of x squared minus 1. But we know that y is positive, and therefore sine y must be positive, so we can reject the negative root possibility. So we've got dy by dx is equal to 1 over sine y. In other words, it's 1 over the root of x squared minus 1. So if y equals cosh to the minus 1 of x, we've got dy by dx is 1 over root x squared minus 1. Finally, if we've got y equals tan to the minus 1 of x, then we know that that means that tan y is equal to x. If we now differentiate that with respect to x, we get sec squared y dy by dx is the result of the implicit differentiation, must equal 1. So we've got dy by dx is 1 over sec squared y. But we know that cosh squared y minus sine squared y is definitely equal to 1. If we divide through by cosh squared y, that gives me 1 minus tan squared y is equal to sec squared y. In other words, sec squared y is equal to 1 minus x squared, because x is equal to tan y. So we've got dy by dx is equal to 1 over 1 minus x squared. So we've got our third result for the inverse hyperbolic functions. If y is tan to the minus 1 of x, then dy by dx is 1 over root of 1 minus x squared. So looking at this result here, if we've got y equals sine to the minus 1 of x over a, then using the chain rule, we can say that dy by dx is going to be 1 over a times by 1 over the root of 1 plus x over a all squared. Pushing the a through into the square root is going to give me a squared times by 1 plus x over a all squared. So that becomes simply a squared plus x squared inside the square root. So if I've got y equals sine to the minus 1 of x over a, then dy by dx is 1 over a squared plus x squared. Similarly, if I have y equals cosh to the minus 1 of x, I know that dy by dx is 1 over root x squared minus 1. Use of the chain rule will give me, if I have y equals cosh to the minus 1 of x over a, then dy by dx is 1 over a times by 1 over the root of x over a squared, take away 1. And pushing the a in through the square root will just give me dy by dx equals 1 over root x squared minus a squared. In other words, we've got the derivative of cosh to the minus 1 of x over a is 1 over the root of x squared minus a squared. And if I have y equals tanh to the minus 1 of x, I know that dy by dx is 1 over 1 minus x squared. So if I have y equals tanh to the minus 1 of x over a, then I have got dy by dx is going to equal 1 over a times by 1 over 1 minus x over a all squared. That's the chain rule again. Now 1 over a is the same thing as a over a squared. So I can write dy by dx as a over a squared times by 1 over 1 minus x over a squared, which simplifies to being a over a squared minus x squared. So we've got, if y equals tanh to the minus 1 of x over a, then dy by dx is a over a squared minus x squared. So we've now established 6 results about differentiation of inverse hyperbolic functions. These results are really useful when we turn them into integration results. So we have immediately from the previous page 6 integration results. So the integral of 1 over the root of 1 plus x squared is going to be sin to the minus 1 of x plus c. The integral of 1 over root of a squared plus x squared is going to be sin to the minus 1 of x over a plus c, and so on. Now these 6 results are incredibly useful, and fortunately they're actually given to you inside your WJC formula booklet. As well as these 6 results, it's worth remembering that you've got some results which involve inverse trig functions as well. And you'll have met those results earlier on in this module. And these 10 results that we've got here, these 10 integration results here, are very useful in integrating a wide variety of functions which don't initially seem to have anything to do with trig or inverse hyperbolic functions. So let's have a look at a few examples. So find the exact value expressed as a logarithm of the integral between 8 and 12 of 1 over root x squared minus 16. So the integral of 1 over root of x squared minus 16 dx is, using our standard integrals that we've just established, the value of cosh to the minus 1 of x over 4 when x is 12, take away the value when x equals 8. So we've got cosh to the minus 1 of 3, take away cosh to the minus 1 of 2. Now cosh to the minus 1 of a value is the logarithm of the value plus the square root of the value squared, take away 1. So cosh to the minus 1 of 3 is the logarithm of 3 plus the square root of 3 squared minus 1. So that is going to be the logarithm of 3 plus root 8. Similarly, cosh to the minus 1 of 2 is going to be the logarithm of 2 plus root 3. So our final answer can be written as the logarithm of 3 plus root 8 divided by 2 plus root 3. For the next example, we're going to try and find the exact values of the integral between 1 and 0.5 of 1 over root 4x squared plus 1 dx, and the integral between 0 and 2.5 of 1 over the root of 25 minus x squared dx. So, for the first one, we've got the integral of 1 over root of 4x squared plus 1. The 4 in front of the x squared is a little bit of a nuisance, so why not pull that out as a factor? So if we take a factor of 4 out of the square root, it becomes 2. So 4 times x squared plus 1 is the same thing as 4 lots of x squared plus a quarter. Pull a 4 outside the square root, that gives me root of 4x squared plus 1 is the same thing as 2 times the root of x squared plus a quarter. So the integral can be rewritten as the integral of 1 over 2 times the root of x squared plus a quarter. Well, 1 over root of x squared plus a quarter integrates to give me shine to the minus 1 of x over a half. But I've still got the 1 over 2 in front of that, so that's 1/2 shine to the minus 1 over x over a half. So what I've got as the integral is 1/2 shine to the minus 1 of 2x. So I've got to work out half shine to the minus 1 of 2, take away a half shine to the minus 1 of 1. Now, shine to the minus 1 of x is the natural logarithm of x plus the square root of x squared plus 1. So shine to the minus 1 of 2 is going to be the natural logarithm of 2 plus root 5. Shine to the minus 1 of 1 is going to be the natural logarithm of 1 plus root 2. So we have 1/2 ln 2 plus root 5, take away 1/2 ln 1 plus root 2, which we can write as 1/2 ln of 2 plus root 5 over 1 plus root 2. For the second integral, 1 over root 25 minus x squared is 1 over root of a squared minus x squared, where a equals 5. So this is a standard integral, and this one is here in this exercise simply to remind you not to forget the results about inverse trigonometric functions and their use in integration. So this one is simply sine to the minus 1 of x over 5 when x equals 2.5, take away the value when x equals 0, and that is sine to the minus 1 of a half, take away sine to the minus 1 of 0, which is pi by 6 minus 0, which is just pi by 6. For our next example, we're going to try and prove that the integral between 0 and 2 of 1 over x squared plus 6x plus 13 is the logarithm of 5 plus root 29 over 3 plus root 13. Now the key observation here is that we've got a full quadratic expression inside the square root, but we can turn that into something much easier to handle if we just use the completing of the square and a simple substitution. So, if we complete the square on x squared plus 6x plus 13, that is the same thing as x plus 3 all squared add 4. So the x squared plus 6x plus 13 is the same thing as x plus 3 squared plus 4. Now, all I'm going to do at this stage is I'm going to do a very small substitution. I'm going to make the substitution u equals x plus 3. Now, if I make the substitution u equals x plus 3, the integral is going to become 1 over the square root of u squared plus 4. I've got du by dx is 1, so du just replaces the dx. And the limits, well, when x was 0, u is going to be 3, and when x is 2, u is going to be 5. The integral of 1 over the root of u squared plus 4 now is one of our standard integrals, and that's just going to give me sine to the minus 1 of u over 2. Now I need to remember then that I've got sine to the minus 1 of 5 over 2 minus sine to the minus 1 of 3 over 2. Sine to the minus 1 of x is the natural logarithm of x plus the square root of x squared plus 1. So what we've now got is the natural logarithm of 5 over 2 plus root 29 over 4. Take away the natural logarithm of 3 over 2 plus 13 over 4. So we've got the natural logarithm of a half of 5 plus root 29 divided by a half of 3 plus root 13. The halves clearly cancel, which gives me the required answer. Now we're going to have to use a given substitution, x equals 3 cosh theta, to find the integral between 6 and 9 of x squared over the square root of x squared minus 9. So if we make use of the substitution x equals 3 cos theta, then that means that dx by d theta is 3 sine theta. So we can say that the dx part becomes 3 sine theta d theta. When x equals 6, theta must be cosh to the minus 1 of 2. And when x is 9, theta must be cosh to the minus 1 of 3. So making the substitution, I've got the integral between cosh to the minus 1 of 3 and cosh to the minus 1 of 2 of 9 cosh squared theta over the square root of 9 cosh squared theta minus 9 times by 3 sine theta d theta. Well, we know that cosh squared theta minus 1 is equal to sine squared theta. So 9 cosh squared theta minus 9 is 9 sine squared theta. Square root of 9 sine squared theta is just 3 sine theta. So what I've now got is I've got the integral of 9 cosh squared theta divided by 3 sine theta times by 3 sine theta. So the 3 sine thetas can cancel each other out before I do any integration. So I've now just got the integral of 9 cosh squared theta. Now, this stage here, I need to remember my two identities, that cosh squared theta minus sine squared theta is equal to 1. Cosh squared theta plus sine squared theta is equal to cosh 2 theta. Adding those up together, I get 2 cosh squared theta equals 1 plus cosh 2 theta. So 9 cosh squared theta is going to be 9 over 2 plus 9 over 2 cos 2 theta. So I've got the integral between cos to the minus 1 of 3 and cos to the minus 1 of 2 of 9 over 2 plus 9 over 2 cos 2 theta. So integrating 9 over 2 integrates to 9 over 2 theta. 9 over 2 cos 2 theta is going to integrate to 9 over 4 sine 2 theta. Now, the question has said we've just got to find the value of. It doesn't say we've got to find the exact value of. So as this question stands, I think an answer correct to 3 significant figures would suffice. So you could use your calculator at this stage to work this integral out. So when theta is cos to the minus 1 of 3, we get the value of 46.116 for 9 over 2 theta plus 9 over 4 sine 2 theta. And when theta is cos to the minus 1 of 2, the value of 9 over 2 theta plus 9 over 4 sine 2 theta turns out to be 21.515. So the value of the integral is 24.6. On the other hand, if we want to be a little bit more precise and get an exact value, then we can go about it by saying, look, if theta is cos to the minus 1 of 3, then we know that theta is the logarithm of 3 plus root 8. We know that cos theta is equal to 3, and that sine squared theta is cos squared theta minus 1. So that would tell me that sine theta was in fact root 8. And that would tell me that sine 2 theta is 2 sine theta cos theta, which is 6 root 8. On the other hand, so the first part, the value when we've got theta equals cos to the minus 1 of 3, has got an exact value of 9 over 2 ln 3 plus root 8 plus 27 over 2 root 8. If we've got theta equals cos to the minus 1 of 2, then going through the same sort of working again, we're going to get a value of 9 over 2 theta plus 9 over 4 sine 2 theta of 9 over 2 times by the logarithm of 2 plus root 3 plus 9 root 3. So at that stage we have got an exact value for the integral. Now it's well worth your while being careful when you're looking at exam questions to see whether they're saying find the value of or find the exact value of. If it doesn't clearly specify the exact value, then an answer correct to 3 or 4 significant figures would certainly suffice. That's fairly monstrous if you've got to get an exact value. It's monstrous, but it's possible. Okay. And with that rather nasty example to finish with, we've finished our look at the calculus of the hyperbolic functions.